Okay, welcome everybody to WESTalk webinar series, Water and Environmental Student Talks. WESTalk brings together leaders on sustainable water and environmental research from around the globe and students interested in making a difference. In next slides, I'm going to show you the lineup of our speakers since January 14. And I'm going to show you a map that it shows how globally our audiences are spread out. And how successful we were reaching our aim of bringing together people around the globe that they are interested in water and environmental talks. So going to this, next slide, for people who are new to WESTalk webinars, WESTalks are a joint collaboration between IC Impacts and UBC Future Water. Both are research centers based in UBC, and IC Impacts is a pan-Canadian research center of excellence, which serves as a new model for international collaboration. And UBC Future Water is a UBC Research Excellence cluster on the future state of water. It focuses on interdisciplinary research at the intersection of law, policy, and governance, and the applied and biophysical science. This slide shows the organizing committee: Abhishek, Fuhar, Jaskaran, Carl, Freya, and myself. We are all from UBC except Jaskaran, who joins us from University of Guelph. And like I mentioned earlier, this map shows our audiences from around the globe. And I think Carl already posted in the chat box. If not, we're gonna post it. This link, please click on the link if you haven't in the past webinars and add your location. We would love to see where you are logging in and joining us. And with this, I'm going to show you the lineup of since January 14, the leaders and experts who supported us in this webinar series. And today, April 15, we have Dr. Samantha Black from HDR company, who's talking about the hot topic of PFAS in drinking water. And we're gonna have more webinars until June 3rd. And after that, it's WESTalk that Carl talked about. In case you missed the previous talks, please check YouTube channel of IC Impact. You can find the videos there and you can watch it. And this, I would like to, before having an introduction of Dr. Black, talk about the WEST conference. Like Carl encourage everybody to register for free. I would like to mention that we have 2 keynote speakers, that they are very prominent and leaders in the field, Professor Sedlak from University of California, Berkeley, and Dr. Boyd from University of British Columbia. Don't miss a chance to listen to these leaders in the field. And with that, I would like to introduce today's speaker, Dr. Black. She graduated from University of Central Florida, and her PhD research focused on the removal of trace organic compound from groundwater supplies using nanofiltration membrane. Currently, she is a water treatment process engineer at HDR in West Palm Beach, Florida. She works primarily on emerging contaminant and applied research projects, including bench scale, pilot testing, and water quality investigation. She works closely with clients to help them overcome regulatory water quality and treatment challenges. With that, I would like to hand it over to Dr. Black. And if you have any questions, please post it in the chat box, and we will have a 15-minute Q&A session after her talk. I'm going to stop sharing here. Please get over.
Thanks. Can everybody see my screen? Should be able to.
Yep, looks good.
Okay, great. Thank you for the introduction. I'm Samantha Black. I'm with HDR, and today I'm going to give a presentation on per and polyfluoroalkyl substances, aka PFAS. And we kind of call PFAS the forever one water chemical because they are not biodegradable. They're very persistent in the environment, and they've been detected around the world. So the first thing I'll do is go over a quick introduction to PFAS for those of you who might not be familiar. Then I'll talk about PFAS occurrence in drinking water, the current regulatory status in the United States. Then I'll go over some treatment options and then talk about some case studies that we've done with various utilities here at HDR. So first, a quick introduction to PFAS. PFAS are found in industrial and commercial applications. In industrial applications, they're used in manufacturing, they're in the oil and gas and mining industry, and in commercial applications, they're found in pizza boxes and popcorn bags. It keeps the food from sticking to the box or the bag. They're found in fast food wrappers. They're also found in your nonstick cookware, and as well as water and stain resistant textiles. So if you have upholstered furniture that's stain resistant, that's due to PFAS. I've heard it's also been detected in other household items like cleaning items or even dental floss. PFAS are also found in aqueous film forming foam, also known as AFFF, and this foam is used to put out petroleum-based fires or oil-based fires. PFAS and PFOA are the two most common types of PFAS. The Environmental Protection Agency has a lifetime health advisory level for PFAS and PFOA of 70 nanograms per liter. They are hydrophobic and hydrophilic. They're highly soluble and stable in water, and this makes them very difficult to remove from drinking water sources, and it makes them very persistent in the environment. But in addition to PFAS and PFOA, there are actually thousands of other PFAS. There are around 40 detectable PFAS compounds, maybe even more, depending on which analytical method that you're using. But in reality, there are thousands. We just aren't able to quantify all of them yet. PFAS-based compounds were originally developed in the 1940s by 3M for use in nonstick applications. Then they started being used in stain and water-resistant products, and then in protective coatings. In the 1960s, they started being used in firefighting foams, the AFFF, and then waterproofing fabrics and agricultural resins. In the 2000s, the United States began the reduction of a few PFAS, and that was around 2002, I believe. Manufacturers stopped using certain types of PFAS, although they were replaced with other alternative types of PFAS. So they stopped PFAS, PFOA, and PFNA, but they did convert to shorter chain PFAS. The drinking water industry has taken several steps towards understanding PFAS. The EPA released provisional health advisories for PFOA and PFAS. We have the unregulated contaminant monitoring rule, and the third version of this rule had sampling from 2013 to 2015 to try and understand PFAS occurrence. I'll talk more about that in just a little bit. And then more recently, the EPA released lifetime health advisories for PFOA and PFAS, as I mentioned before, that's 70 nanograms per liter. In 2019, the EPA released the PFAS action plan to respond to PFAS, and I'll talk about that in just a couple slides as well. I am by no means a toxicologist. I just wanted to point out some of the bigger takeaways that have been conducted with respect to PFAS toxicity. Essentially, PFAS can adversely affect organ and hormone toxicity, immunotoxicity, neurotoxicity, and mitochondrial toxicity. So that's why we have these health advisory levels, and that's why removing PFAS from drinking water has gotten so much attention over the last several years. So next, I'll go into PFAS in drinking water. This is just a simplified diagram showing the PFAS cycle. So really the primary sources of PFAS are manufacturing. So when a manufacturer uses PFAS, it gets disposed of either through air emissions or discharged to a stream. PFAS can also enter the environment if aqueous film forming foam is used at an airport or an oil tank farm that has a fire. or it can end up in the groundwater when we throw away consumer products like our used pans or old clothes that have water resistant properties. When we throw this away in a landfill, PFAS can leach from the products into landfill leachate and sometimes end up in groundwater. Wastewater treatment plants and water treatment plants are really just conveyors of PFAS. They're not producers of PFAS. So wastewater plants can receive wastewater discharge from a manufacturing site, and then if the wastewater plant discharges their effluent to the environment, then that's just another way to convey PFAS throughout the environment. I mentioned the unregulated contaminant monitoring rule earlier, and during sampling, so if you're not familiar with the UCMR, basically it requires utilities in the United States to sample for up to 30 contaminants in their finished water. And during UCMR 3, which was 2013 to 2015, there were 6 PFAS included in UCMR. And during this sampling campaign, many utilities unexpectedly found PFAS in their drinking water. So the first step for these utilities is to evaluate where the PFAS is coming from, where their contamination source is. And many states have actually started sampling campaigns to try and identify the major contributors to PFAS contamination. This map shows results from UCMR 3 showing PFAS and PFOA detections throughout the United States. So many states have PFOA and PFAS, but during UCMR 3, there were some states that didn't have any PFAS detection. However, there are some drawbacks to UCMR 3. They only looked at 6 PFAS, and we know that there are thousands, and we're now able to quantify around 40 to 50 different types of PFAS. And during UCMR 3, the analytical limits were relatively high compared to the analytical techniques that we have available today. So for UCMR 3, we could detect 10 to 90 nanograms per liter of PFAS, but today we can actually detect all the way down to the single digits. So actual occurrence has been much greater. PFAS has actually been detected in 49 states. I think Hawaii is the only state that has not had PFAS detection. There has been detection at military sites, drinking water sites, and what the Environmental Working Group calls other known sites. So those could be airports or landfills or wastewater treatment plants. And this link on the bottom left is from the Environmental Working Group. You can actually go on their website, and this is an interactive map. I just took a screenshot. And you can actually look at these results in even more detail if you wanted to. So now I'll get into the current regulatory status. And my familiarity is with the EPA and the United States, so I'd really be interested to hear what you all know about PFAS regulations in your area after this presentation. So as I mentioned, the EPA has published a PFAS action plan. This was published in 2019 and updated in February of 2020, and focuses on a few areas, including source water protection, contamination cleanup, drinking water risk communication, and improving the understanding of PFAS. So contributing to PFAS research either through treatability research or improving analytical techniques to identify PFAS. One of the major outcomes of the action plan is that the EPA released regulatory determinations for PFAS and PFOA. This was released on January 19th of 2021. The highlights from the regulatory determinations are that PFAS and PFOA will become regulated. This is about a 2-year process or even more after the final regulatory determination. So that was January 19th. So the next step is for the EPA to propose a drinking water regulation. That'll be in about 2 years from now. And then about 1.5 years from that is when we'll get the final drinking water regulation. There were no regulatory determinations made for PFAS beyond PFAS and PFOA, but it is possible that other types of PFAS might be regulated or consider being regulated before the next regulatory determination, which will be in 2026. There are several statewide actions for drinking water, and because we don't have a whole lot of toxicity information, and because there's not a whole lot of known guidance out there, like from the EPA giving us a regulation, many states have actually imposed their own regulations. There are 6 states that have regulations, and they're all a little bit different. For example, New Jersey has regulations for PFNA, PFAS, and PFOA of 1313 and 14 nanograms per liter. But other states like Massachusetts are regulating the combined total of 6 types of PFAS. So instead of looking at regulating just 1, 2, or 3 PFAS individually, they're regulating several combined. And there are other states that have action levels or reporting levels and guidelines, and others have screening levels, and this is just for drinking water. There are other actions that are out there for groundwater. So now I'll get into some treatment options, some drinking water treatment options. There are several ineffective treatment processes for PFAS removal. Conventional treatment, which is coagulation, flocculation, sedimentation, and filtration, is really not effective at all at removing PFAS. Lower pressure membranes like microfiltration and ultrafiltration do not remove PFAS. Dissolved air flotation doesn't either, and ozone and UV light also provide very minimal PFAS reduction. The 4 processes that have shown to be effective for PFAS removal are powdered activated carbon and granular activated carbon. They remove PFAS through adsorption. Ion exchange can also remove PFAS, and then high pressure membranes, including reverse osmosis and nanofiltration, can remove PFAS. So first I'll go over powdered activated carbon, or PAC. There are several advantages to using PAC. It can be implemented quickly within a matter of months because these systems are pretty standard. You can buy them from an equipment supplier and have it delivered to your water plant, and then you just need to get it permitted and hooked up. It can be used intermittently if you have seasonal problems. It's often used for seasonal taste and odor compounds like MIB and geosmin that vary throughout the year. It's a relatively reliable process and a small footprint. The unit shown here treats, I want to say, 8 mgd. It's a relatively low capital cost, at least compared to the other alternatives I'm going to go over. And it has other secondary water quality benefits. It can remove total organic carbon, which contributes to disinfection byproducts, which is another regulated water quality parameter. Some disadvantages are that you really only get low to moderate PFAS removal. You really can't get complete removal. And PAC is really only good at removing the longer chain compounds. I didn't go over the difference between short chain and long chain PFAS, but short chain and long chain just refers to how many carbons are in their molecular structure. So PAC is better at removing the longer chain compounds, up to 80%, depending on how much PAC is added to the water, whereas it can really only remove up to 40% of short chain PFAS. Other disadvantages are that there's competitive adsorption. So the adsorption sites are finite, meaning PFAS will compete with other organics in water for these adsorption sites. It has an impact on residuals at the water treatment plant that will need to be disposed of, and then these residuals will contain the PFAS that were absorbed onto the PAC. PAC can be messy, requires frequent maintenance, and is a relatively high operating cost because you have to keep purchasing PAC over and over again as it's used. Granular activated carbon is another adsorption process. There are a variety of applications. You can use pressure vessels or gravity filters. It just kind of depends on your site layout, what you have already existing at your water plant, and your other water quality goals. You can get pretty high PFAS removal with GAC of both short chain and long chain, but GAC is much more effective at long chain PFAS removal compared to the short chain PFAS removal. So it really depends on the type of PFAS you have in your water. PFAS and PFOA are both long chain PFAS. It's the only process that can completely destroy PFAS, and that's because once the GAC media has absorbed PFAS, this media can be incinerated, and then the PFAS are destroyed in that way. Some of the disadvantages are that the backwash water, when you backwash GAC, needs to be disposed of, although you don't backwash GAC very often, much more infrequently compared to a traditional sand or anthracite media filter. But media replacement might make GAC cost prohibitive, depending on the type of PFAS in the water supply. Ion exchange operates pretty similarly to GAC. Instead of using an adsorptive media, it's a resin. You can get pretty high PFAS removal, and manufacturers are actually coming out with PFAS selective resin to kind of help with the competitive absorption. Like I mentioned, for PAC and GAC, there are organics that can compete with PFAS for those absorption sites, but ion exchange can be manufactured in a way that it makes it PFAS selective. It's a pretty reliable process and has a relatively short contact time compared to GAC, which allows the vessels to be smaller and allows fewer vessels compared to GAC. Ion exchange has a moderate capital cost and other secondary water quality benefits if you wanted to get the removal of other water quality parameters. But just like GAC, backwash water for ion exchange must be disposed of, although you don't backwash very often, and it's generally not recommended to backwash ion exchange, although it is sometimes needed. And then resin replacement, just like GAC, might make ion exchange cost prohibitive depending on the PFAS in your water supply. Ion exchange has shown to be a little more effective with respect to long and short chain PFAS removal, ranging from 55 to 97% removal for long chain, and then depending on the short chain compound you're looking at, you can get up to 95% removal. Reverse osmosis and nanofiltration are two types of high pressure membrane processes. They have a variety of applications. They're most often used in, well, RO is most often used to treat brackish water or seawater, whereas nanofiltration is used in freshwater applications. You can get pretty high removal of PFAS, both long chain and short chain, pretty good removal of both of those. They're reliable, they are a small footprint compared to the other technologies, and you can get other secondary water quality benefits. And one of the major advantages is that you don't have that competitive absorption like you do for PAC and then sometimes ion exchange. Some disadvantages are that you have to dispose of the concentrate stream. So the way membranes work are you have feed water going into the membrane skids, and then depending on the percent recovery you're able to get using membranes, you'll have a majority of the water going on to become finished water that contains minimal or low amounts of PFAS, but some water ends up in the concentrate stream or the reject stream, and that needs to be disposed of, and it will contain high levels of PFAS. It contains everything that's rejected. Other disadvantages are membranes require pre-treatment and post-treatment. There's the potential for membrane damage of scaling or fouling, so it's important to have the pre-treatment and post-treatment in place. Membranes are energy intensive and a relatively high capital and operating costs. Now I'll go into some case studies that we've done at HDR. The first case study was done for the city of Greensboro in North Carolina. Essentially, they found PFAS in their watershed during the unregulated contaminant monitoring rule. So we helped them with a watershed investigation where we conducted sampling for 2 years at 30 different sites, both groundwater and surface water, to try and understand where PFAS contamination was coming from. And we eventually did pinpoint the contamination was coming from near an airport. They had high PFAS concentrations one summer. So we actually did a powdered activated carbon bench scale study for them and then designed the full scale PAC system. They were able to get 20 to 30% of PFAS removal. They could have gotten higher, but the more PAC you add to your system, the more residual handling issues you can have, because you have to remove that PAC after it's added and absorbed the PFAS. It has to settle out in your settling basins or remove during your filter backwash and get removed. So they didn't want to add any more PAC than they absolutely had to. But all of this led to a fate and transport study. We have a modeling team in our New Jersey office, and they actually did some modeling to determine PFAS transport through the watershed, so from the contamination site through the lakes and then to the water treatment plant to try and understand any weather impacts, weather conditions that can influence PFAS variation, because they did find that PFAS was very variable in their raw water. Another project that we're currently working on for the same utility, the City of Greensboro, is the advanced treatment of emerging contaminants. We actually have started working on this project about 4 or 5 months ago. We're doing a preliminary alternatives analysis to identify the best treatment processes for PFAS removal for their site. So we're looking at GAC, ion exchange, and RO and NF. They currently use PAC, but as I mentioned before, it's a high operating cost. They're not getting as much removal as they really want to, and they would like to implement a process that can remove other emerging contaminants as well, should those become a problem in the future. So right now we're doing bench scale testing of GAC and ion exchange. We'll be starting a pilot for GAC, ion exchange, and membranes later on this year, and then we'll roll into final technology selection after the bench and pilot testing are done. Then later we'll do 30% design, final design, and then eventually we'll construct this new system at their water plant. Another case study was for the Cape Fear Public Utility Authority in Wilmington, North Carolina. We did a GAC and ion exchange pilot study for them at their aquifer storage and recovery site. These are just some photos of the different pilots we had. We had 2 larger pilot vessels, an ion exchange vessel, as well as a GAC vessel. We had different sampling ports throughout the bed. So water comes in from the top, and we wanted to be able to capture PFAS breakthrough as it moved through the ion exchange and GAC bed. We also had 4-inch mini columns shown on the bottom right. And we were using these, we were able to look at GAC and ion exchange in a lead lag configuration, so operating in series. We found GAC performed a little bit better than ion exchange for this particular application, but they have so many PFAS in their aquifer storage and recovery site that it's cost prohibitive to use either of these technologies. So right now they're actually not even using their ASR site. They're just relying on the other 3 water plants that they have until they can either come up with the funds to treat this water, or they'll have to pump water out of the ASR well and dispose of it. Another really cool project that we finished about a year ago was these guidance documents that we developed for the American Water Works Association. There are 3 of them. One is on drinking water treatment for PFAS selection. Another is a source water evaluation guide. And then we have a summary of PFAS toxicological research. I believe these are a free download if you're an AWWA member. And with that, I would be happy to take any questions.